2, 1. All right, let's get going. I am excited because now that we have firmly established the set of real numbers, we will now begin the process of getting into the calculus. So we are now going to begin proving all of the wonderful things that we learned, not only in just Calc 1, but also, as you can see, Calc 2. So it's quite interesting. In the calculus experience, you run into sequences and series at the end of Calc 2, and it's the sequence part especially, it's only maybe a few days, and then you spend almost all your time on series, which we're going to get to. That will be next week. But it turns out there's a lot going on with sequences that we really just don't even address in calculus. So, you think you might know sequences, but oh, you're gonna find out there's some juicy stuff here, and I'm very excited, as hopefully you can tell, because we are going to begin with what I think is probably one of the most important proofs you're ever going to see in your life. That being said, in the second sequence video, we are going to see what is without a doubt probably the most difficult proof you will ever see. So, kind of a double-edged situation here with sequences, but without further ado, what exactly is a sequence? Okay. Alright, well, the sequence is quite simply just a function from the natural numbers to the reals. And that's it. No more, no less. There's literally nothing else to say. A sequence is a function that you give me natural numbers and I spit out real numbers, right? And traditionally, sequences are exclusively written in the index notation for functions. So we write x sub n, x going from 1 to infinity like this. And again, this is indicating that I have a function so that when you give me input, this is the output, right? And this represents not only just announcing that there is a function, but also this is itself a set. It is the range of that function. Beautiful. Okay, so now, of course, as always, and as we've noted, there's no reason to start at 1. You could start at 0, and in fact, there will be times for that, but for the most part, we will always start at 1. Again, you can start at negative 15. It really doesn't matter. You just need to start somewhere. And yeah, that's it. So, there are many sequences that you undoubtedly have ran into in your life, and many that we will see. The main thing that we care about with sequences in analysis, and honestly in calculus, is whether or not they're convergent. And so let's talk about that. So formally, we say that a sequence, so again, I've announced a function from the natural numbers to the reals, we say that it converges to an element in the real line if, given an epsilon, there is a capital N such that this is strictly less than epsilon, and that holds for all n greater than n. Alright, so here is our first taste of an epsilon argument. In the next video, I will reveal who you can direct all of your anger towards for creating the epsilon notion of convergence, so you can have a name. And right, so here's our first taste of it, and it will absolutely not be our last, right? Because again, this expression right here is pretty much if somebody asks you what analysis is, this is it. This is it. So let's break down what this is saying and why this is right. Because again, right, when we said the real numbers are a totally ordered field with least upper bound property, right, we spent a good amount of time talking about, well, why is that even right? And as we saw, right, all of the natural things about real numbers that we have taken for granted, we now have formal rock-solid proofs for why things work the way they do, why the square root of that 2 is the thing, all that fun stuff. So again, a sequence here, we're saying converges to x if the following happens. Given an epsilon, you can think of this as like a tolerance, right? Give me a really small number. Note, it can be really big too, but, right, it's arbitrary. If you give me a tolerance, if you give me any amount, no matter how small, then at some point in the sequence, the terms of the sequence are no further away from this real number x then epsilon. And they stay there. So a sequence converges to a real number x if the sequence eventually gets close and stays close. Right, and that sounds like a pretty good idea for capturing the notion of convergence, or the idea of limit, which we'll get to in a moment. Right, so, right, give me epsilon, give me 1 over 10, give me 1 over 100, give me 1 over 1,000, give me 1 over 10 to the 1,000. At some point, if a sequence is converging to something, its absolute value, its difference, this quantity right here, right, which, when we talked about absolute value, right, we noted that it's kind of measuring how far away you are from 0. This is saying that the distance between the real number x sub n and the real number x can be made as small as you want, and not only can it be made small, it stays small. So note that you would need this part of it as well. Because if you just said given an epsilon, there's an n so that we get close, well, it could be that there's one m that works, but then after it, it gets far away. So we need a point in the sequence where we get close, and we stay close. And the get close can be made as arbitrarily small as you'd want it to. So that sounds pretty close to how we are taught limits in calculus, right? The output of the function gets as close to the target as an input does something nice, right? So again, sequence is just a function, so again, these secretly are limits. So the definition here sounds legit, but there's something subtle to this that maybe you don't notice it, but your brain does. The way it's phrased, a sequence converges to a real number. I didn't say it converges to its limit, right? I've given you an explanation of how a sequence can get really close to a real number. What's not built into this is any sort of uniqueness, right? This just says we converge to some real number if all of this goes down. So a natural question that you need to address is, all right, well, suppose there were two things that we converge to, are they different? Right, and at first, maybe you don't think to even check that, because you would just go, oh, well, I'm converging to something, right? There is nothing in this definition that says that what I converged to was unique, right? And that really goes against kind of how we first learned this in calculus, where we're like, the limit of the function is this, or the limit of the sequence is this, right? You're presupposing that what it goes to is unique. But note, in the definition, there's nothing there saying that it is unique, but as we are about to see, the definition ensures uniqueness. And this first proof that we're going to do here, like I said, to me, I think is probably the most important proof you're going to see in this course, because it demonstrates and illustrates quite a few common ideas and techniques, not only just in analysis, but in proofs in general, and also, I think, thematically grabs what pure mathematics is all about. So to me, this is a very important proof. It's not a difficult proof at all, but what's being communicated here I think is very important. So if you're really going to pay attention to one proof in the course, please let it be this one. Okay, now that's a very bold claim for a proof that's 2 slides and really doesn't have a lot going on in it, to be honest, but it does demonstrate quite a few common techniques. So the first thing to note, of course, and one of the reasons I think this is one of the most important proofs you'll ever see, is that it's verifying something that before you really start doing rigorous mathematics, it's forcing you to stop and really think about everything. Because when you talk about limits, you're automatically going into that with, like, this is a unique thing. Right, but if you really think about what the definition is saying here, there's nothing about uniqueness that's guaranteed. Uniqueness is demonstrated, so it is representing, I think, that level of pedanticness that we need to embrace in rigorous mathematics, because, again, kind of our goal is I want to derive as much as I can from the least amount of assumptions. So it's forcing you to think of that. So before we even get into the proof, I think there's a valuable lesson there. All right, and now let's get into the proof. So, like every proof, pretty much from this point forward in the course, we will begin with everyone's favorite phrase, let epsilon be greater than 0, or given an epsilon greater than 0. Now, what I'm doing right here is just unpacking my hypotheses. I'm assuming that my sequence converges to x, so that means at some point it gets as close as I want for all n, and now note, I snuck in a epsilon over 2. Epsilon times 1/2 is a positive number. Now remember, like I said here, this is arbitrary. This could be any positive number. So this is a very common maneuver with epsilon arguments where you sneak in an epsilon over 2. Right, and note here I snuck it over there, and then you might be going, well, why? What's the point of the epsilon over 2? That'll become apparent in a moment. All right, so in this first sentence here, we just unpack the definition of what does it mean for x sub n to converge to x, and what does it mean for x sub n to converge to y. Okay, now note there is an n that works for this, and there's an m that works for this. So what we're going to do is take the maximum of these two. So I'm going to let j be the maximum of n and m. Some authors, our textbook included, whenever they've got two convergent things, they'll do like an N1 and an N2. I like having different letters for clarity's sake. But, you know, so you can do like N sub 1, N sub 2, and have this equal N. That's pretty common, but I like using different letters. I think it visually is different, so your brain kind of recognizes that. Alright, so now this is another common move that happens. You have a finite amount of things, and you take its maximum over its minimum. In this case, we got two things, and we can just pick their max. Alright. Now, j, by construction, is bigger than n, so we know that x sub j does not, gets within epsilon over 2 of x. And similarly, j is also bigger than m, because j is the maximum of these two. So x sub j here gets within epsilon over 2. Now note here, this is another little trick that we pull a lot. Remember the idea of convergence is, given a tolerance, I get as close as I want and I stay close. Here I'm using the and I stay close part of it by just going, well, I have a j that I know works, so I can plug that in. I'm totally allowed to plug in capital N here. Right? Likewise, I'm totally allowed to plug in capital M, right? 'Cause it satisfies the inequality. So it represents another trick that we will see quite a bit. So we've already encountered 3 common maneuvers that happen, especially dealing with limits of sequences, but also generally in analysis, where you have an epsilon thing, and you sneak in 2 epsilons. You have a couple of things running around, and you take their maximum or their minimum, which we will see later in the course, and then using the inequality here to plug in a specific value to produce these. Alright, so those are 3 common maneuvers, and now we get a 4th one, the triangle inequality. So we look at x minus y. Well, actually 5 even, wow. So first things first, we sneak in a plus 0, where I've cleverly chosen what 0 is equal to. I then invoke the triangle inequality, and these were chosen so that they were epsilon over 2 plus epsilon over 2, and thus we get an epsilon. Alright. So, like I said, there's not too much difficult things going on right now, right? Because if you really look at what we've done here, again, it's not super deep. It's really just unraveling of definitions. The first time we're pulling off this take the maximum of 2 things trick. Unraveling definition again. Our first time really invoking the triangle inequality, and I think our first time of seeing the add 0 trick. So yeah. Alright, so one thing I want to comment before we go any further here, this epsilon over 2 maneuver, this is a bit more modern. If you go to, like, even an analysis book from, like, the 70s, what people will do is, this is the trendier thing to do of, these are referred to as 2 epsilon proofs, because I have an epsilon over 2 and an epsilon over 2, and I add them together to get an epsilon. Back in the day, people didn't actually do the 2 here. They would just get here at the end and have 2 times epsilon, and then they would say, well, epsilon was arbitrary, so 2 times epsilon is arbitrary, so we're done. So this epsilon over 2 is a bit more modern. Okay. Now, claim that we're done, so let's remind ourselves of what we're actually proving here. What we're proving here, again, is that if a sequence converges to two things, those two things must coincide. And what have I established so far? Well, I have established that the difference in absolute value of the two things that I have assumed we converge to is less than epsilon. And as we noted, when we think about epsilon here, epsilon's a tolerance. Epsilon is a really small positive number. Epsilon can be 1 over 10. It can be 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 10 to the million. So this is saying that this real number right here can be made as small as I want. Now, remember, absolute value is the square root of the input squared. So it is a square root of something, so it's always non-negative. If it was strictly positive, since we demonstrated that x minus y is always strictly less than epsilon for any positive epsilon, well, if this is strict here, if this is not an equality, then this is a strictly positive quantity, so I can plug it in here, but that's contradictory. You can't do that. Right? And again, like I said, when we first encountered this in ordered sets, you're going to be shocked at how often you actually use this thing as a contradictory tool. You've got a real number strictly less than itself. So it's got to be the case that this is actually equal to 0. It can't not equal 0. All right, and an absolute value is equal to 0 precisely if what I have is equal to 0, and the only way I got this equal to 0 is if x and y are the same thing. And there we go. I have proven that if a sequence converges to two things, those two things must be equal. So if a sequence does converge to something, whatever it's converging to is unique, and thus that's what I can truly call its limit. Nice. All right, and this slide represents... like I said, this proof overall is a lot of common ideas in analysis and just common proof ideas. This one, again, really represents... another idea that we use a lot in math is this idea of abstractification. Right? The epsilon here was just any positive number. For any epsilon. Right? For all. And using that, we showed that a thing that's bigger than 0 has to be always strictly less than any positive thing. And that enforces that this has to actually be equal. So one of the key differences between algebra and analysis, which are sort of the two big branches of mathematics, algebra is all about setting things equal to stuff, and analysis is all about getting things less than them. And sometimes they fuse together because I actually want equality, but I can't directly get it, so what I get it with is an inequality. So here we see another thematic piece of mathematics on display. The sort of, I want equality, but, right, I don't have it, so I'll use inequalities to get there. So, well, there we go. There's our first proof involving sequences, and there was a lot to unpack there in terms of broader points and broader techniques that are going to be not just applicable for this course, but also just in general, like, right, so much of abstract mathematics is highlighted here in these in this proof. All right, so again, let's do a quick little recap again of all of that. So sort of initially, the whole reason here of the definition didn't say anything about uniqueness, so we're actually proving that. So again, the pedanticness. Oh god, what's going on? My computer's freaking out. Hopefully that's not messing up the video. Doesn't seem to be. Anyway, so this trick of multiple epsilons showing up, so this, like I said, is sometimes referred to as a 2 epsilon proof. We will, later on, see a 3 epsilon proof. The largest one I saw in a class was a 5 epsilon proof. That was a proof of something called the Arzela-Scully theorem. The largest number of epsilons I've ever seen was at a conference once on function spaces at the Southern Illinois University at Edwardsville, SIUE. An absolutely insane person did a 10 epsilon proof, so that was his entire talk. It was 10 slides, and each slide was showing how one part of a thing was less than epsilon over 10. And, yeah, it was a sweet proof. I don't remember anything about it, I just remember that it was a 10 epsilon proof, and I was like, this is absolute mad lad. It was great. Alright, but yeah, so the 2 epsilon proof, the trick of picking a maximum of a finite set, also a minimum. The trick of adding 0, the triangle inequality being the most important thing ever, and then the final point here of demonstrating inequality by showing an inequality works for an arbitrary type of number, in this case strictly positive. So 0 here is not special. You can replace this with 5, and that would give you a number, forcing a number to equal 5. So sort of like, the number is bigger than 5, but it can't possibly be any strictly bigger than 5, so it must actually equal 5 then. That idea on its own, the sort of, I have a lower bound, and I know that anything strictly bigger than it, this thing has to be smaller than, so this must equal 5. That idea has been around since Greek mathematics. Specifically, Archimedes knew that, and he used that idea to compute areas of parabolas, where sort of he had a, I know the area is no more than this, and anything strictly less than it, it has to be bigger, so the area has to equal that. So when he was stuffing triangles underneath under a parabola to get its area. So that is a very ancient idea in mathematics, predating algebra itself. Yeah. Okay, so like I said, this proof doesn't really, in terms of content, it's not a lot, but it's really highlighting a lot of powerful techniques and powerful ideas, which is why I'm spending so much time gushing over it. It is, like I said, one of my favorite proofs in terms of just its instructive value. It's not my all-time favorite proof. I don't think we'll actually... I think we might offhand mention my all-time favorite proof when we get to continuous functions. But maybe we'll even do it. I don't know. We'll see. It's a little bit beyond the scope of the course, but anyway. All right. So let's keep going. So, previous lemma, previous proposition. That's what I'm calling them. I mean, again, there's no distinction between proposition. All right. But previous prop, get the alliteration going. Anyway, so by the previous result, if a sequence converges to something, whatever it converges to is unique, so we can now say a sequence is convergent if there's something it converges to, and the unique thing it converges to is its limit, and we denote it as we have seen before, limit as n goes to infinity of x sub n. So again, the intuitive idea of as n gets bigger and bigger and bigger, this gets closer and closer to some specific real number. That intuitive idea now has a precise statement involving epsilons and m's, and whatever it's going to, as we've just verified, must in fact be unique. Beautiful. Alright, so the stuff that we've seen in calculus, we've now put it on much firmer standing. So naturally, we now want to start studying it further, and so the remainder of these slides is going to be sort of just a quick little kaleidoscope, a brief little vignette, a collection of some results that you probably saw in calculus, but now we're actually going to give them solid proofs. Okay, so let's start with a great one, which is the limit as n goes to infinity of 1 over n is in fact equal to 0. So in other words, as n gets really big, 1 over it gets incredibly small. Alright. Okay, so let's straight up do this proof. The limit of 1 over n is equal to 0. So, let epsilon be greater than 0 strictly. Okay, now, as we verified by the Archimedean property, I can find a capital N so that 1 over capital N gets strictly less than epsilon. Right? We proved this as a consequence of the Archimedean property. Archimedes appearing twice today. Alright, well then if I give you any n bigger than capital N, now note, in order for this to be the limit, I need to show that the absolute value of the difference of the sequence and my proposed limit gets less than epsilon. Well, if we clean up the algebra here, that's just 1 over n. N is bigger than capital N, so 1 over n is less than or equal to 1 over capital N, just cross-multiply there. And 1 over capital N was chosen to be strictly less than epsilon. And there we go, given an epsilon, there is a capital N, so that for all n greater than n, this absolute value difference gets strictly less than epsilon. And there we go, we've officially proven something you learn in calculus, right? It's something that is intuitively true to you, right? Even before that, even before you took calculus, if I said, what happens when I put a bigger and bigger number in the denominator, you would go, oh, the number gets smaller and smaller, so as n gets bigger and bigger, this whole thing is getting closer and closer to 0. Right, so that intuitive idea was already in your brain. We used it in calculus to great effect, and now here we see a clean and precise argument for why it's true, relying on key properties of how the real numbers behave. Good stuff. Beautiful. All right. Let's keep going. I'm having a good time. All right. So a good thing to do whenever a definition is given, so a sequence being convergent, meaning that it has a limit, it's always a good thing to then give an example of something that doesn't work. Right? So we establish a definition, we give an example of something with a limit. Let's now produce something that doesn't have a limit, right? Because if everything had a limit, then it's not a definition, right? It's just a tautology. It's always true, right? So it's good to show when you have a new definition that something works and something doesn't. So that means there's this barrier to be studied, the sort of the edge of, what is the fundamental difference between convergent and divergent. So having two examples, right, gives us some feel for it. 1 over n, of course, sort of visually we can imagine, 1/2, 1/3, 1/4, 1/5, slowly getting closer and closer to 0. And -1 to the n here, well, as n cycles between even and odd numbers, this is going to bounce back and forth between 1 and -1. So the sequence never stays somewhere. It always bounces back and forth between 2 points. All right. So let's formally prove it. Now, the good news is, if you want to prove something is divergent, well, suppose it's convergent and cause a problem. All right, so suppose it does have a limit, and this is going to represent something I'm going to do a lot, which is be lazy with the notation. The understanding here is that this is the limit as n goes to infinity, based on the notation, but I don't like it, especially when I have an inline equation like this. If I do put in the n goes to infinity in the notation, so for example, if I wanted to actually do that in LaTeX, it's building here. Yeah, it does that, and there's a way to fix it using a command called underset, but it's really, yeah. So when I have an inline like that, I don't include the n to infinity. And that's pretty common. You'll see people be lazy with that. So I like being lazy. Cool. All right, now suppose it does converge. Let's let L be its limit. Now, if it does converge, that means that the sequence has to get arbitrarily close to L and stay arbitrarily close. Now, epsilon can be any positive number, and since I'm trying to show something is not convergent, I just need to find one thing that causes a problem. I don't need to show that for all positive epsilon there's a problem, or I could show that for this one that we're going to see an issue. All right. So if the limit does exist, then I can get -1 to the n within 1 of L, and that's good for all n bigger than capital N. All right, but I kind of already let the cat out of the bag, because, as I noted, for even powers, this always spits out 1, because -1 squared would be -1 times -1, which would give you 1. So the squaring here guarantees that this is just 1 to the n, which is always going to be 1. And 2 times n is always greater than or equal to n, so 1 minus L then is strictly less than 1. And likewise, 2n plus 1, that's an odd number, and -1 to any odd power is going to give you back -1. Now again, we didn't explicitly prove that, right, but as I noted, we weren't going to be exhaustive with every property of an ordered field. You can verify it, you can prove it to be true, if you so care, but right, the whole point of establishing all this stuff was to basically go that all of the arithmetic things that we know to be true are still true. So, again, there's some things we can take for granted, and this is one of them. Alright, anyway, so now what do we have? Well, now I've got -1 minus L is also strictly less than 1. So I have that L is strictly less than 1 in distance away from 1, and strictly less than 1 in distance away from -1, but -1 minus 1, the distance between those two numbers, is 2. And again, here we see the sneaking in plus 1, the triangle inequality, and once again, oh hey, look, 2 is strictly less than itself. Again, you are going to be shocked at how often you use that. It seems like such a basic thing. Nothing is strictly less than itself. It is unbelievable how much you use that very simple fact to demonstrate significantly more and more complicated mathematics as we go on. So, Alright, beautiful. But there we go. Now we have an example of a sequence which fails to converge. -1 to the n is a divergent sequence. The story doesn't end there, though. A little bit more on that in the next round of videos, but let's keep going. Okay. So, something that we care a lot about with sequences is whether or not they're bounded. Okay. So, a sequence, again, is a function. And when I write this, I'm announcing what the function is, right? It's x sub n, you give me the input, that's what I give the output for. I can also create its range, the set of it, right? So this and this are technically the same set, although, like I said, with the index notation, this is announcing it, and then this is stressing the set consisting of these things. But anyway, so a sequence is said to be bounded above if the set of values is a bounded above subset of the reals. It's bounded below if the set of outputs of the sequence is bounded below, and bounded if it's both bounded above and bounded below. So it turns out that a bounded sequence can be characterized using absolute values, and since we are using absolute values in our conversation of convergence, this seems like a pretty reasonable thing to take a moment and prove. Alright, and this is a great example of a proof where it's an if and only if, but you really only need to do one of the ifs and then be lazy and go with the only if is similar. Okay, so suppose that we have a bounded sequence. That means that I have an upper and lower bound for the set itself. And here we go again with the trick of setting something to be the maximum of two things. Now note I made the lower bound negative, and hopefully it's going to be clear why I need that because of an absolute value showing up. Alright. So, B is the maximum of these two things. Now, that means negative alpha is less than or equal to B, which means negative B is less than or equal to alpha. Alpha is an upper bound for the set of values, so x sub n is always less than it. Beta is an upper bound, so x sub n is always less than beta. And B is bigger than negative alpha and beta, so beta is less than B. Hey, there we go, x sub n is greater than negative B and less than B, so its absolute value has to be less than or equal to B. And the converse, then, is similarly proven. You just basically read this backwards, because this guarantees that this holds, and that gives you an upper and a lower bound, respectively. Beautiful. Alright, so this turns out to be a nice little characterization of bounded using absolute values, which again, as we've already seen, we use absolute values in sequences to talk about convergence. So naturally, we are now going to connect all of this back to convergent sequences. So a sequence converges. If it does converge, it must be bounded. Now, this gives you a nice way of detecting if you have a non-convergent sequence. If its values get arbitrarily large or arbitrarily small, well, then there's no way we can be converging, because anything that converges is bounded. Now, intuitively, right, the idea of convergence is that your sequence gets close to a limit, and it stays close. So let's let L be the limit. Then at some point the sequence gets within 1 of L. So that means if I let B be the maximum of all of the absolute values up until the point that we get close to L, and then throw in an absolute value of L plus 1, well, now for any n there are two possibilities. If n is less than or equal to capital N, then, right, it's just less than one of these, so that's what we have there. X sub n is less than B, because the first n of them we're just throwing in. Now note, this is a finite list, so it must have a maximum. Now, it could be that the list is incredibly long, but, right, at some point the sequence has to get within 1 of L. Okay. Now, if n is greater than n, then, if I look at the absolute value of x sub n, I turn into some capitals for no good reason, as all good things do. Okay. Now we sneak in plus 0 once more. We invoke the triangle inequality. This quantity right here is guaranteed to be less than 1 because n is bigger than n. And hey, we've got 1 plus L, which B is chosen to be the biggest thing out of all of these, so it's definitely less than or equal to B. So there we go. X sub n's absolute value was always less than or equal to some value B, and there you go. We gotta have a bounded sequence. Beautiful. So, like I said, this ends up being not necessarily used all the time. This is a pretty good check for verifying divergence. If you have an unbounded sequence, you just have divergence and we're done. However, note that the converse of the statement is not true. You can have a bounded sequence that fails to be convergent. -1 to the n, for example. So, boundedness does not immediately tell us anything about convergence, but it turns out that if you do have a bounded sequence, there's a lot that you can still do. So, specifically, as we're about to prove here, if I have a sequence that is monotonically increasing and also bounded above, then it's got to be convergent, and furthermore, it converges to the supremum of this set right here. Beautiful. Right, now, so no, being bounded above means that this set is bounded above, and since it's a non-empty bounded above set, it has a supremum, because of the least upper bound property, and now we'll prove that in fact it is the limit. So this ends up being a very powerful tool, because, I mean, we're going to use this a lot. And also note that this actually gives you kind of a really powerful tool, because you're going to be shocked at how often we're going to find a sequence that is bounded above and monotonically increasing. So this guarantees that whatever that is, it is convergent. And in fact, we have a formula for what it converges to, the supremum. So this is a very powerful technique, and it will be used very frequently. Okay. And in addition to being a powerful technique that's used very frequently, it's also a really fun proof. This is another one of my favorite proofs. A lot of the proofs here are... all the proofs in this class I love for the most part, even the ones that are like horribly pedantic and not super interesting. This one's cool, I like this. This one has a very neat little trick. Okay, so as noted, we're bounded above and non-empty, so this has a supremum, so let alpha equal that. Alright, I want to show that now that we converge to it, the supremum. So given an epsilon, let's find the capital N. A, let epsilon be greater than 0. Okay, now alpha is the least upper bound for this set. So alpha minus epsilon is positive, so if I subtract epsilon off of alpha, well, this is strictly less than alpha, which means that what I have here is not a upper bound, which means there is some point in the sequence that will surpass this value, right? Otherwise, this wouldn't be the least upper bound. Alright, so at some point, there is a capital N, the sequence gets bigger than this, so given an epsilon, I have to find my capital N. So note, I found my capital N by using a property of supremums, that this is the least upper bound, so anything less than it fails to be an upper bound. Alright, now let n be bigger than capital N. This, we know, is less than or equal to x sub n as by choice. I'm monotonically increasing, so n, which is bigger than capital N, x sub n is bigger than that. X sub n is an element of the set here, so it's less than or equal to its supremum. And now subtract everything by alpha, and we get negative epsilon is less than or equal to this. Is strictly less than, sorry, that's supposed to be a strict right there. Let's fix that. Epsilon is strictly less than x sub n minus alpha, which is strictly less than epsilon, so the absolute value is less than epsilon, and thus my sequence must converge to the supremum. Beautiful. Good proof. And again, hopefully you're starting to get into the rhythm here, because a lot of the proofs of sequences converging are all kind of very similar. They all begin with let epsilon be greater than 0. Our main task is to now find the capital N that works, and then use the hypotheses to guarantee the absolute value is less than epsilon. Right? And again, like I said, I like this proof. I think it's fun. For a variety of reasons, it's using, again, all of the hypotheses in kind of a very unique way. Right? Bounded above gives me a sup. Okay. Now, given an epsilon, which I need for the definition, the way I can invoke a positive epsilon and a sup to interact with each other is by taking the difference. I'm also assuming monotonically increasing, which gets used exactly once. So the bounded above giving me the sup, the epsilon for the limit, Combining the epsilon and the soup part gives me the capital N that I need. The monotonicity guarantees that the N bigger than capital N is going to behave the way I want. And then how absolute values work comes in and finishes the proof off. So a lot of wonderful little bits of information coming together. It's always a good thing. What I'm doing right now when I'm talking about proofs like this, when you complete a proof, go through and again, just sort of dissect what are the big moments of the proof and how are those moments related to my hypotheses. Are there ways of tightening up the hypotheses? Right? Is there anything special about real numbers here? Natural questions to be asking. It's always a good thing to do. Like, when you complete a proof, go back through it and go like, all right, what really happened there? Like this. Yeah, and hopefully you're starting to feel these epsilon proofs. They're spicy. I love them. They're so good. Yeah, my analysis course ruined my life, and my goal is to do the same to you. So, in a good way, right? Maybe not. We'll see. All right. Well, I'm hungry, so let's keep going. Okay, so here is a classic theorem that we see in calculus, and we're going to actually prove it. So let's say I have two sequences. They converge to the same thing, so the limit of the sequence of A is the limit of the sequence of B. And let's say I have a third sequence that stays between the two. Alright, well, that sequence has to converge, and specifically it has to converge to one of these values, whatever they may be. So, a little earlier I mentioned an epsilon over 3. That's technically what we're going to do here, but this is more of an epsilon over 2 and an epsilon over 4. And note epsilon over 3 would be in between the two. Alright, but so we're going to prove something that we saw in calculus, which is that if I have three sequences, the one on the left converges and the one on the right converges, and they converge to the same thing, it's got to be that whatever's on the inside, whatever's between, must ultimately converge to the same thing too, right? The values of x sub n get sandwiched between the limit of an and the limit of bn. Right. But, right, that intuitive idea makes a lot of sense and works for us. We need to prove it, so let's prove it. Alright, so before we get the epsilons in, let's kind of do this proof a little bit backwards. Let's start with the ending. Right, I want to prove that this converges to this, so I obviously have to work with this at some point. So here, before we do any epsilon stuff, we're working on the proof backwards. So we do our sneak a term in trick and invoke the triangle inequality, which from this point forward, I'm just going to kind of streamline those things. Alright, and then now what? Well, now let's start using our hypotheses. X sub n is bigger than A sub n, so their difference has to be not negative, so their absolute value just goes away. X sub n is less than B sub n, so that's how I get this inequality. The absolute value of something is always less than or equal to the number itself, so that's where we get this inequality. Alright, and now here I sneak in a add 0, but again, I'm being very clever about how I choose 0. Okay, and then once more we invoke the triangle inequality to pick up this, and here we'll pick up twice this. Now note, in the absolute value they are opposite ordered, but remember, absolute value is multiplicative, so the absolute value of something times -1, which is what this is, would be the absolute value of the original. The absolute value of -1 is 1. So, right. Cool. So, before we even get into any of the epsilon stuff, for any n, we know that x sub n and the limit of a, we always have this inequality right here. Okay. And note, this explicitly used the part of the hypotheses where the limits are the same. Now note, before we finish off the proof, we are done. Right? Intuitively, we're done, because the absolute value here, this is going to get arbitrarily small, and so is this. But note, there are two of them here, so given an epsilon, we can find an m and an m so that these get as small as we want. But this one we're going to make less than epsilon over 4, and this one we're going to make less than epsilon over 2. And then do our... Oh, hey, why is that not aligned correctly? Let me fix that. And then our usual, take the maximum of these two things. Then for anything bigger than the max, then n is bigger than n, and n is bigger than m, so this gets small, and so does that. So here's the epsilon over 2. 2 times epsilon over 4 gives me epsilon over 2. They add up, and we get epsilon right here. Okay. So, like I said, in older books, they didn't care to make the proof end nicely with an epsilon. They were content with the proof here ending where, note, it would end with a 3 epsilon. So you actually could have done epsilon over 3 here and gotten the same effect, or epsilon over 3 and epsilon over 4 and epsilon over 2, like I did, also get you an epsilon in the end, however you want to make it work. But yeah, there we go. Sandwich theorem proved, and again, a classic thing that we learn in calculus, and once more a thing that you'll be shocked to see we will use quite a bit. So it's a good thing we took the time to prove it. Alright. Okay, so, like I said, we're kind of doing now that we've got limits of sequences on pretty firm ground, we're kind of just going through and doing a little sample. We're sampling the platter of all of our classic calculus results. So next up, one of the things I want to prove is one of the algebraic results, which is that if I have 2 convergent sequences, the product converges to what you think the product should converge. Now, I picked product to be the one we prove, because this one's got a real tricky bit to it. It turns out that the sum of 2 convergent sequences is convergent, and it converges to the sum of the limits, but that proof is really boring. That proof is just like triangle inequality, and that's it. You don't have to do anything creative with it. Product here, though, on the other hand, is this is a technical proof. And I like technical details. I don't know about you. Alright, so I chose to do this one. You could do the same thing for sum. You can also do quotient, and you can also do difference. Difference is not too crazy, and once you see how product works, you can figure out how quotient works as well. Quotient's the worst out of the 4. Proving the quotient of a sequence converges to what you think it should converge to is... it's a little messy. So we'll see here that the way that sequences were defined was based off the absolute value of the difference. Now that means we're dealing with the absolute value and the additive structure. So the fact that the multiplicative structure works the way you want it to, at first glance, seems like maybe that wouldn't necessarily work. If you're just purely going off of how it's created, it was created with the additive structure. Now, the multiplicative structure interacts with the additive structure via the distributive property, but, this is kind of one of those results where, even though you might, from calculus, go, like, intuitively it makes sense, from the analysis standpoint, the way limits are designed is with additive structure in mind. So having the multiplicative stuff work, it's not immediately obvious why that should be true, right? Like, again, you walked into this class and you knew this fact to be true because you see it in calculus, but it's deceptive. That's in my opinion, an example of your math intuition. You're not exactly being on a firm ground, right? Because while your brain might just go, this should be true, why wouldn't this be true? Right, really think what convergence means again. It doesn't really have anything to do with multiplication, so this actually is kind of shocking that this is still true. In a way. But yeah. Okay. That being said, let's do the proof. And like I said, the proof here is a little bit more involved because this is a great example of a proof that starts with something, and it's not clear at all why you need this until you get to the actual ending of the proof, and it's like, oh, good thing I had that. Alright, so we're going to first note that since y, the y's, is a convergent sequence, it's got to be a bounded sequence, so there's some capital B, so that's true. And something that we didn't explicitly note, but we actually need right now, is that the B that exists can be chosen to be strictly positive. Right? And you can choose to be strictly positive just by adding by, a big enough number to make it strictly positive. Right? No, B here has to be greater than or equal to 0, so just add 1 to it. Now it's strictly positive. Right, but note, in the details of the proof that we did there, at no point did we actually say anything about whether or not B is positive or not. Note it's built into it, but We're going to see a moment right now where we need it to be strictly positive. Okay. So, what do I want to prove? I want to prove that this converges, so give me an epsilon, I gotta find a capital N, so that things work. And, excuse me. Alright, yeah, so here we see, this proof starts with some shit. And this is like, sure, bro, I bet that works. Right, so here's maybe your first encounter of a proof where there's this stuff in the beginning that's like, okay, I bet. And let me tell you, this is not going to be the worst that you'll ever see. This is all stuff that's like, at first glance, like, okay, yeah, I bet this works, and then as we're going to see in the next slide, it works perfectly. But yeah, this is the long-standing tradition of math proofs, having some junk in the beginning that doesn't quite seem like you need it until we get to the part when you need exactly this stuff. And like I said, this looks bad. This is still not even going to be the worst, I think, even in this course you're going to see. And it's certainly not the worst you're going to see in your life. I recently saw a proof of something, and the opening line of the proof aggravated me so much that I immediately went out of my way to come up with a completely different proof of it, which took me about a month to do, by the way. If you're interested, email me, I'll tell you all about it, but, or do a WebEx. But anyway, alright. Okay, so given an epsilon, we want to find our capital N. Well, we're using the convergence of these to produce an N and M, so we're going to take the max of those two. But what we need them to get less than are these things. So note, here's where we're seeing we need the B to be strictly positive in order for this to make sense. This here is always greater than or equal to 0, so if I add 1 to it, it's strictly positive. And again, it'll be clear what this is. The epsilon over 2 is hopefully the least mysterious part of it. The B right now is, okay, why, and this is also a, like, okay, why this? But now as we see, those are exactly what we need. So, we do our usual thing where we let J be the maximum of the N and the M we got from our hypotheses. So now we're looking at the difference of the product of X and Y versus the product of the limits. Here I sneak in 1, and note how I snuck 1 in. Y sub n is hanging out here, and the limit of x sub n is hanging out there. So note, I needed to sneak in a mixture in order to isolate these two things. And the multiplication introduces these two. Okay, so now here we see, it should be a B, not an N down there. Let me fix that. Right. There's a B right there. Alright, so now here we see why we needed to point out that y sub n was bounded, and why we even needed to prove that in the first place. So here the B will cancel out that B, and that gives me an epsilon over 2. And now here we see why I needed to sneak this in, because now I've got this absolute value of this real number. This fraction right here, note, I don't care what the actual absolute value of this is. This will always be greater than or equal to 0. And it's always strictly less than 1. So actually, that's actually not a strict right there. That is a less than or equal to. It could equal 0. And then thus you just get 0. But yeah, no, this never exceeds 1. Right? Because the limit of x sub n is always strictly less than this. So, alright. And so that this quantity is always less than 1 strictly. And then epsilon, well, actually, no, it is strict. It is strict, even if it is equal to 0. I'm psyching myself out. Ignore the change. Keep it there. Yeah, this quantity is always strictly less than 1, and it's always non-negative, and this is always non-negative as well. So when you multiply the two, you'll get that. But anyway, this quantity right here, x over 1 plus x, never exceeds 1. So I can multiply by epsilon over 2. Epsilon over 2 is strictly positive, so the inequality isn't ruined. And there we go, epsilon over 2 plus epsilon over 2, and we're done. Yay, epsilon. Alright, nice. So, like I noted, modern math proofs and analysis especially, and especially with epsilon arguments, we like to end with the epsilon. And part of the problem now is that when we start the proof, there's this, like, junk that we do in the beginning that's not quite clear until you get to the end, where it's like, oh, that's... So, like I said, that's a bit more of a modern thing to make the ending of the proof be an epsilon. If you go back to an analysis book from like the 40s or the 50s or the 60s or even the 70s, the way this proof would have been done would have just been, okay, you get an epsilon here, you get an epsilon here. This is bounded by some number b, so you'd have b plus this number and all of that times epsilon, and then they would go, epsilon can be made as small as you want, so this limit converges. So they don't even try in those older proofs to try to have this really precise cleanup of the epsilons, which you can argue maybe is a little bit of a better thing, but there's something to be said about getting this sort of very precise, clean answer here in the end. But all right, beautiful, and we got one more thing. So I got one more piece of calculus lore to explicitly prove, which is that for a real number strictly between -1 and 1, if I start raising it to the nth power and seeing where that goes as it goes to infinity, it goes to 0. So, for example, we already know 1 over n goes to 0. Now we're going to prove that 1 over 2 to the n would go to 0. 1 over 3 to the n goes to 0. 1 over 5 to the n goes to 0. Yes. And now note, obviously we cannot include -1 because we know that doesn't work. And 1 can't be included because 1 to the n is equal to 1, so that actually converges to 1. Alright, so this is our last bit of calculus lore to prove. And what I love about this one is, I actually have an interesting relationship with this one, because this was one that I don't think I actually saw the proof of this in my calculus, in my my analysis course. I think it was just brushed over. And then when I was studying for my analysis exam in grad school, I remember pausing and going, oh wait, shit, how do you prove 1 over 2 to the n goes to 0? And I was like, wait, how do you actually prove that? I was like, wait, I don't think I ever saw proof of that. So I went to my professor and I asked, like, how do you prove that? Like, how do you do that with epsilons and stuff? And he just looks at me and goes, yeah, Bernoulli's inequality. And I was like, okay. And so I left. Then I immediately Googled Bernoulli's inequality. And I was like, what the hell is this? I've never seen this before. So, hey, here's Bernoulli's inequality. So Bernoulli is a name that you've most likely encountered at this point in your life, probably in differential equations, but maybe in another course you took, not necessarily math. The Bernoullis were a very wealthy family in the 17th century, 16th century? I forget what year exactly. But the Bernoullis were a very wealthy family, and thus they were a very well-educated family, and there were a bunch of them. And in mathematics, we actually have two Bernoullis. We've got Jacob and John. And I'm forgetting which one gets the credit here. It's probably John, or Johann, I think officially. Seems to have done more mathematics. Jacob also. The Bernoulli brothers are quite interesting in mathematics. There is a branch of math called the calculus of variations that only exists because they were trying to one-up each other with difficult math problems. So look into that. That's a fun little story. All right. Anyway, so here's Bernoulli's inequality, which you may have actually seen in your proofs course, because this is a great induction problem. This is a very, and in fact, Lebel, the writer of our textbook, has this in his chapter 0 homework as a induction example. And he's like, hey, prove this by induction. And yeah, it turns out it's actually not a bad induction. And now note what the inequality says, just sort of visually. It says that this line is always less than or equal to this power function. Whenever x is bigger than -1. So that makes a lot of sense if you think just visually. You just write, hey, here's a straight line, and then here's, x squared, or x cubed, or x to the 4th, and it's like, clearly that's going to overpower it. And it's not immediately obvious how this is related to this. So, like I said, my professor, when I asked him, wait, how do you actually prove that 1 over 2 to the n goes to 0? And he just said Bernoulli's inequality. And I looked it up and I saw this and I was like, oh god, how do you connect it to that? You can kind of maybe see it, or you're like, oh, I got a 1 maybe. But actually, when you see the proof, it's really not exactly clear how it comes into play. But let's go ahead and work out the details of the proof for this. And like I said, it's inductive, so plug 1 in, it works. Alright, that's it. Base case done. Alright, now suppose that it works for some natural number k. Now suppose that, and I should probably, for some k in the natural numbers, probably want to actually include that in the statement here. Right, to indicate that we're doing induction. Not that, yeah, we're not inducting on, like, something other than the natural numbers. That'd be crazy if you could, like, induct on dyadic rationals or something, which you totally can. Oh, god. In fact, any countable set you can sort of do an induction on. And actually, in fact, on any set you can technically do an induction. It's called transfinite induction. Ugh. Yeah, let me induct using the real numbers. Yeah, you hold my beer while I do that. Alright. Anyway, yep, so, alright, suppose that we got this working. I want to prove it works for n plus 1. Now, hey, I got a hypothesis. I should probably, use it. Alright. So, indeed, we are going to use it because I have this, and I'm going to multiply that by 1 plus x, obviously, and to get the k plus 1. So, that's why I need the greater than -1 to get it to be positive, so I can multiply and not screw up my inequality. Now, note, if you read the proof left to right, there's this mysterious part right here of, oh yeah, this is always greater than or equal to 0, so let me sneak it in. And it's not obvious why you would do that, but if you read it from the right to left, it makes a lot of sense, because if you just multiply this by 1 plus x, well, here I've got what I want. I have the k plus 1. Here, if I multiply this out, I have this, and I need to connect it to 1 plus k plus 1 times x. Now, you just go, oh, k is a natural number, and x squared is always greater than 0, so, yeah, if I add this, I'm just making it bigger. So this is an example of, like, reading the proof from right to left is actually a bit more, like, natural, right? So the way you would have done the proof without, you know, if I just said, hey, go prove this, you would start with this, and then work your way that way. But of course, when we write proofs, there's always a sort of, like, unnatural beginning, and then a natural ending. Right. And then obviously we then get what I want. I have the inequality for k plus 1, so it's true for 1, and if you suppose it's true for any k, we can prove that it's true for k plus 1, so by induction it's good for all n. Beautiful. Now, side note, you can actually generalize this. It turns out that there are things other than natural numbers that this works for. So there actually is a much stronger statement to be made here. Yeah. But I'll leave that for you to look into. Alright, anyway, let's wrap things up, finally, with our final bit of calculus lore about limits. We will prove that c to the n converges to 0 whenever c is strictly between -1 and 1. So there's actually 2 cases we gotta do. Which maybe isn't too shocking, but it's worth noting that we have to deal with the case of c equals 0 separately. Now, if c is equal to 0, then c to the n is equal to 0 for all n, which means if you give me an epsilon, right, well, I can make that equal to 0, so that's strictly less than epsilon. That's good for all n bigger than 1. It's just good for all n. There you go, definition satisfied. So, as a side note here, technically what we've proven is that we've proven that every constant sequence, so any sequence that always spits out the same output, any constant sequence is convergent, and converges to whatever the constant is. So we've actually proven something a little more general here that we will use. Right, the limit of a constant is just the constant, which, again, you know from calculus, but now we actually kind of see a solid proof of it. Okay, so the case of c equals 0 taken care of. So now let's suppose that c is not equal to 0, and as always, do some random shit for reasons that becomes clear later on. Alright, so obviously note I need c to be non-zero, otherwise you got a problem. Alright, so I'm letting x equal this, but why? Okay, well, add 1 over, cross multiply. Oh, hey, my good friend, 1 over 1 plus x. Hey! That's showing up again. I wonder if that's like a very common theme in analysis or some junk. Beats me. Anyway, so note, the real reason I set this up is that now I've got the absolute value of C is equal to this, which, as we've already noted, is strictly less than 1. Sorry. And since by hypothesis the absolute value of C is less than 1, this quantity right here, since I know this is strictly less than 1, that forces a couple of things here to be true, specifically that x itself is always bigger than 0. So since C is less than 1, 1 over C minus 1 needs to be strictly positive, and note that means x is bigger than negative 1. Now, why am I pointing that out? Well, we just did Bernoulli's inequality, where you need x to be bigger than negative 1 in order to actually invoke it. Okay. Alright, so here we see why I needed the C not equal 0, artificially. And we got our absolute value of C is equal to this expression, and this expression was created using an x that's bigger than negative 1, so Bernoulli's can apply. Alright, now let's actually finish things off. Given an epsilon greater than 0, we know 1 over n converges to 0, so at some point 1 over n will get less than x times epsilon. X is positive, so x times epsilon is also positive, strictly. So, and since 1 over n converges to 0, it can get less than that at some point. And now we use Bernoulli's. Okay, so C to the n minus 0 is the same thing as the absolute value of C to the n. Absolute value of a product is the product of the absolute values, so I can pull out this n here. Absolute value of C is 1 over 1 plus x, so I raise that to the nth power. And now we see, I know this by Bernoulli's is less than that, so 1 over it is less than this. Likewise, x sub n is less than 1 plus x, 1 plus n over x. So that means 1 over it is less than it. And here I just cross-multiply the x back over, and I get that that's less than epsilon, and the proof's over. So, like I said, Bernoulli's gets used, but it kind of gets used in a weird way. 1 over it is what actually gets used. So I remember, like I was saying, when I was studying for my analysis exam in grad school, I had that brief moment of like, oh wait, how the hell do you actually prove 1 over 2 the n goes to 0? And my professor just told me Bernoulli's inequality. And it takes a little bit to see how you would actually use it. You're kind of like, oh, I gotta use 1 over it. Interesting. But there you go. Beautiful. So, whew, there's our first little taste of sequences. And so, like I said, not exhaustive. Certainly there are a bunch of other results we could prove that I've mentioned for here, but we've seen some solid proofs of some things, and hopefully you're feeling a little confident in your own skills of proving some convergence of sequences. Alright, now with this one in the bag, we have 2 more videos and sequences throughout this week. And each one's going to be, I think the next one might be about as long as this one. Maybe it'll be shorter, we'll see. The third one is going to be super short because we've done a lot of legwork already. But alright, so there we go. Next up, we're going to look at subsequences. So we can look forward to in the next video. With that, see you next time.